In this meeting, past Past President Bill Bonnet and retired Hawaiian Electric Executive shared his observations and stories from his 1960s summer jobs when he worked on the early atomic energy programs at the Nevada Atomic Testing Site. He talks about the tunnel complexes and individual tunnel designs used for the underground atomic testing. He talks about Operation Plowshare, that was a potential peacetime use of atomic blasting, and the role of the Sedan Shot, which he witnessed. It was the last surface test in that program. During Bill's final summer, he worked on the Rover Program, which had the objective of designing and building a nuclear reactor which could be used as a rocket engine. Please send us your comments. Mahalo.
It's a pleasure to introduce a friend and a colleague, president of this organization, I think back in 1979, so some time ago. Bill attended Vanderbilt University, graduated with a bachelor's in civil engineering, went on to do a master's a few years later at Illinois. In the meantime, his entire family moved to Hawaii, and Bill commuted back and forth until he actually took a permanent job here in Hawaii with Austin Smith. Russ Smith, a very well-known person of my and Sam's generation, Bill's generation, very outspoken engineer, brought him to Hawaii permanently. He worked several years for Austin Smith. Then he joined the administration of Eileen Anderson. He was kind of a guy that public service was pretty high in his priorities. He and Mike Chun ran the Department of Public Works, I think it was called then. And following that assignment, he joined Hawaiian Electric, I believe as Director of Engineering first here on Oahu. And then he went to Maui and eventually became president of Maui Electric, retiring, and now he enjoys his time doing a lot of hiking, all kinds of places like California. So Bill, we're going to let you roll ahead with your presentation. Looking forward to it.
Great, I got a lot of ground to cover. So the time I'm going to cover is the summers of 1962, 1963, and 1964, when I was a summer hire at the Nevada test site. Two of those summers were with a company that had been contracted to create and maintain the tunnels which would be used for underground nuclear testing. The third summer was with Edgerton, Germishausen, and Greer, EG&G, working on the Rover Program, the development of a nuclear rocket engine. Back to the test site and the testing. Remember, following World War II, that we were never sure how much the Russians knew about where their program for atomic development was. And as a result, there was great urgency in testing and development by the US of its nuclear capabilities. So the earliest testing was done in the Pacific, Marshall Islands specifically, Eniwetok and Bikini Atolls. But the logistics of that made it a very slow program. And it was having evident social and environmental impacts. So as a result, the Nevada test site was created. In 1950, Harry Truman authorized the acquisition of 680 square miles, which you see as the Nevada test site here. That was later enlarged to 1,350 square miles. So if you've ever flown from the West Coast to the East Coast, you look out your plane window and you see an awful lot of desolation. There wasn't a lot of relocation involved in that land acquisition. So the Atomic Energy Commission was designated both to develop and manage the programs for the Nevada test site, to determine what needed to be done and how to do it. So the first test was a surface test conducted in 1951. Now, as you can see from the lower right, the Nevada test site is 65 miles northwest of the city of Las Vegas. looking more closely at that, where did the testing actually happen? You see Mercury in the lower right, but it's 30 miles up to Area 12, which is where both the underground and most of the surface testing was actually done. Let's take a closer look at that. Some terms that may be familiar to you. Yucca flats and Frenchman flats. Most of the testing was done in Yucca flats, and to the left of Yucca flat, you'll see a designation called Rainier Mountains. This is a mesa. Okay, here's your surface testing area, Yucca flat. Here is Rainier Mesa. The Yucca Flat has an elevation of just over 4,000 feet. The Rainier Mesa, adjacent to it, goes up to 7,700 feet. So you, in a very short span there, have an elevation difference of over 3,700 feet. So what that means is that if you tunnel into that mesa from the flats, you've got a substantial overburden to contain both the energy and the contamination from underground nuclear testing. So it was ideal for the underground testing purposes. Some background information. There have been 1,021 nuclear tests conducted at the Nevada test site. You can compare that through roughly the year 2000 with 2,121 known tests worldwide. And by seismic activity, you got a pretty good idea of what other people were doing. So what that means is that essentially half of all of the nuclear tests that have ever been conducted anywhere in the world have been conducted at the Nevada test site. So atmospheric tests have totaled 873 megatons, million tons of TNT, of which 545 have been fission, the splitting of plutonium or uranium-235 and the release of the energy that accompanies that. The remaining 300 and something have been fusion, thermonuclear, the transformation of hydrogen into helium and the release of energy which accompanies that. So the largest atomic, for reference, the largest known atomic detonation in history was a Russian, 58 megatons. Absolutely unimaginable. This is a picture of the largest US detonation, Castle Bravo in Bikini Atoll in 1954. This detonation, this was intended to yield energy of 6 megatons, and it actually yielded 15 megatons. So as you can see, there was a lot of uncertainty about what the yield of a given amount of fissionable material was going to be. And that was one of the things they were trying to learn from the underground testing, where you could contain both the energy and the contamination. The largest test at the Nevada test site was a 104 kiloton Sedan surface shot in June of 1962. I was able to witness this with binocular, with special sunglasses and binoculars from a distance of maybe 5 miles away. This was the last surface test. The Nuclear Test Ban Treaty was signed in 1963. So already there was an awareness that this was going to happen. So this was the last surface test, and thereafter all testing, nuclear testing, was underground. For comparison, the yield, I said this was 104 kilotons. The yield of the plutonium bomb that was dropped on Nagasaki was 15 kilotons. And you know what the devastation was that did. And Hiroshima was a 20 kiloton atomic bomb. So this is 104 kiloton. The underground testing, there were already a lot of tunnels before the underground testing began. And the reason for that is that it's always been and continues to be recognized that for nuclear waste storage, there is no better place than the tunnels in Rainier Mesa. So there was, in anticipation of the need to store nuclear waste, this tunnel system had begun some time ago, and I was able to wander through many of these. This is a single tunnel complex, G tunnel. So this wasn't tunneling back 100 yards and going somewhere else. These are extensive tunnel complexes. I have no idea what was done here, but I was impressed with the scale of the tunneling. The tunnel that I became familiar with and that the company I was working with was responsible for was much more like this. Beginning, you see, at the portal, and then you have a main tunnel, dimensions, I would say maybe 15 feet by 20 feet high, approximately, from my recollection. And then you take a side tunnel off the main tunnel and you almost link it back on itself. And that is ground zero. That's where the detonation occurs. The idea being that that explosion will seal itself off and contain both the energy and the contamination. Now, in June of 1963, I witnessed a shot, a detonation at J Tunnel, and we were all down in the parking lot below the tunnel portal, and they had the loudspeakers counting down 4, 3, 2, 1, and what normally is just a big boom. Well, in that instance, it did not blow across and seal. It blew back around and out the tunnel portal, and anybody who could get in anything with wheels got in it, and got out of there, and we were decontaminated for 2 days following that. It was an interesting experience. So one of the things that most interested me was the tunneling. I was working with tunnel engineers. These are people who had experience in gold mines, copper mines, transportation tunnels. These were people whose lives and profession were tunneling. And to work with them, to see both the art and the science that converged in their work was just really interesting. But geology dictates the method of tunneling. Normally, when we think of tunneling, we picture the big, full-faced tunnel, hard rock drilling machines. But the geology at the Nevada test site is what's called volcanic tuff, TUFF. It's kind of like the lava that we know here, but it's been compressed over thousands and thousands of years. But still, it is a relatively soft material, and it's not structurally suitable for full-face boring because it would not be self-supporting, and a machine would have a problem with that. So the approach in material like this to tunneling is to drill, blast, ventilate, and muck in 4 stages. The variables to be considered in drilling and blasting: the location, the diameter, the depth, and the spacing of the holes that you're going to put your gelignite into. The angles at which those exist are drilled relative to each other, because your intent is to pull from that face only what you want. And some of those holes that you drill don't have charge in them. Because think about it. When the blast is detonated, it's done sequentially, microsecond differences between a blast here and a blast there. So what you want to do is provide a path of least resistance for that energy, from charged holes into more central vacant holes, and pull that face outward. So it's fascinating to watch all of this, and what it does mean is that your drilling for these holes is a very precise operation. And this is what's called a jumbo. This is the drilling machine that is used, and you can do multiple holes with that. But it does give you the spacing, the size, the depth, the angle that is absolutely critical to your achieving your end result. So what does it look like in practice? So here you see the locations have been identified, and the jumbo is just beginning its drilling work. And you can see that you have to follow that round that you pull out. Once you've mucked it, you got to put some supports in there. This is not a self-supporting geology. And not always can you pull the whole round out. Sometimes you have to put in a pilot tunnel. Sometimes you actually leave a column in the center to support the key of the arch, and you have excavate only your side tunnels and then come back and do that later. This particular method here is called header and bench technique. Then there is the ventilation. Once that round is blown, you got a lot of carbon monoxide out there. So before anybody can get in there and work again, that's got to be ventilated very, very well. So two kinds of ventilation, and it's not like a transportation tunnel, where it's in operation all the time. This is kind of a batch operation. You blow and then you ventilate, and then you look for the time to clear the carbon monoxide level at the face in order that people can actually get in there without a great risk and resume their work. So the best way to do that, you can have forced ventilation or you can have extraction, positive pressure or negative pressure. The most effective and the least time to clear carbon monoxide from the face of the tunnel is extraction with a jet fan at the floor. The ceiling extraction, jet fan at the floor. So you're creating a circulation at the tunnel face.
You need a big air mover for that.
Yeah, you do. Because the efficiency of your operation depends upon being able to get back and work that face again. This I want to show you. This is an 8-minute video from the archives.
Sedan, a 100-kiloton nuclear cratering detonation, recently executed as part of the Atomic Energy Commission's Plowshare program. Plowshare envisages many uses for nuclear explosives, including applications in nuclear excavation, mining, production of useful isotopes, and power. Nuclear excavation is, however, the most straightforward application and the nearest to practical usage. The chairman of the Atomic Energy Commission has recently established within the Plowshare program a research goal to determine the feasibility of nuclear excavation within approximately the next 5 years. Project Sedan was the first step in implementation of this program. The basic objective of Sedan was to determine the cratering effects of a deeply buried, high-yield nuclear explosion. Previous experience with 1 kiloton and smaller explosives has shown that as a nuclear explosion is buried deeper and deeper, crater size steadily increases until a depth of burst is reached for which crater dimensions are maximum. Below this depth, crater size decreases. Also, as the explosion is buried deeper and deeper, the fraction of the radioactivity released to the atmosphere becomes less and less. Thus, it is possible to choose a depth of burst that will give almost maximum crater size with the release of only a few percent of the radioactivity. Using these concepts, the depth of burst chosen for Sedan was 635 feet. The predicted crater diameter ranged from 1,200 to 1,500 feet, and the depth from 180 to 315 feet. The release of radioactivity was expected to be less than 4%. The explosive used for Sedan was a 100 kiloton thermonuclear device in which less than 30% of the total energy came from fission. Since only a few percent of this fission fraction escaped to the atmosphere, less than 2 kilotons of radioactivity was released by Sedan. The site of Sedan was the Atomic Energy Commission's Nevada test site, located in southern Nevada, 70 miles northwest of Las Vegas. The specific location chosen for Sedan was at the north end of Yucca Valley, near the site of 2 earlier nuclear cratering detonations and much high explosive cratering work. Sedan was detonated at 10 a.m., July 6, 1962. This is a view taken from the top of a 1,500-foot tower located 6 miles from ground zero.
Moving out at the
These sequences are being shown at about 1/3 normal speed. The base surge, seen forming here, continued to grow until it covered an area about 5 miles in diameter. The main cloud rose to a height of 12,000 feet above the desert floor.
So that rolled up onto the mesas.
I think the farther away than that.
This close-up view was taken from a ground station 3 miles from ground zero.
Had to do with the direction of the wind.
The dome rose to a height of 290 feet before it vented at 3 seconds. This long view gives a better picture of the mass of material moved by the explosion and the early stages of cloud formation.
That's the Rainier Mesa in the background.
A very large fraction of the radioactivity that escaped from Sedan was mixed with the fallback in the crater area. Thus, the cloud carried only a small fraction of the radioactivity. The area covered by the base surge is clearly discernible in this aerial view by the pattern of light-colored dust. The crater is about 1,200 feet in diameter and 320 feet deep. The lip ranges in height from 20 to 100 feet. The predictions and the results compare favorably. The fallout pattern from Sedan extended almost due north from the crater area. Shown here are the 5/10 Renchten and 3.9 Renchten isodose lines. These correspond to the total dose a person would receive assuming continuous residence. The highest dose received by any off-site resident was 2/10 Renchten. These isodose lines represent the dose one would receive assuming entry into the area 1 week after the shot and continuous residence thereafter. Research is being done on nuclear explosives with so little radioactivity that excavation projects will be possible with no off-site radiation problem. Large-scale excavation projects, such as harbors and canals, require the use of explosives in the range from 100 kiloton to over a megaton. Sedan has been a major step forward in the nuclear excavation program by extending our cratering experience into this high-yield range.
So Operation Plowshare, potential peacetime uses, and moving large amounts of earth, of course, was one of the most evident potential applications. Specifically, was the North American Water and Power Alliance, a concept developed by the Ralph M. Parsons Company under contract to the Army Corps of Engineers in the 1950s. This would have involved 369 separate construction projects to divert 75 million acre-feet per year from various rivers in Alaska and Canada to the western United States via the Rocky Mountain Trench, a natural formation through Canada. So here is a specific example of the thinking that was involved in the Plowshare program. Detailed calculations have been made of how much and where these nuclear detonations would be needed to redirect that fresh water and essentially meet all of the anticipated future water needs of the western United States. This concept died under its own weight. If you can imagine the politics involved in this, this is Canadian water that's going to be brought for the needs of the Western United, and that was always difficult. But it was too big, it had too many players, and then there was the emergence of environmental laws. The National Environmental Policy Act came about in 1970. So this whole idea was pretty well abandoned in the early 1970s. But because thinking and our values had moved on since the 50s, everything was possible for nuclear energy. I should have mentioned that when the testing first began at the Nevada test site, you could see the shots from Las Vegas. And for the first 2 or 3 shots, which were not announced, because this was secret stuff, the call, test site and the AEC were inundated with what's going on. So they began to announce that these were going to happen. And in order to avoid the wind, which would occur as the land heated up, these tests were pre-dawn. So this this was wonderful. The casinos began to hold pre-dawn parties. And tourism boomed. Everything in Las Vegas was named atomic. Atomic nail file salon, nail service station, nail bar, atomic bar and grill, atomic wedding chapel. Yeah, everything was atomic. It was that age. But we did move past that, and by the 70s, those signs and those names came down and no longer exist. The concept of the Rover project was the development of a nuclear-powered rocket engine. It began as an Air Force project to develop a nuclear power upper stage of an ICBM, but it was recognized early on that the potential of that was well beyond the upper stage of an ICBM. The concept, as you know from nuclear reactors, these are big things. These are heavy things, incompatible with compressing to the point where you could put it into a rocket, make a rocket engine out of it. So the concept, which was originally developed by a man named Robert Bussard in 1953 in Oak Ridge, where I was living at the time, was to use liquid hydrogen at minus 253 degrees centigrade as both coolant and propellant for this engine. And a nuclear moderator, a neutron absorber for the nuclear core. And that nuclear core is at 2,230 degrees centigrade. So think about the advances in material science that would be required for that temperature gradient between a reactor core and very close to it, the liquid hydrogen coolant. Interesting challenges in material science. So following Sputnik in 1958, the space race was on, and the concept of Rover was transferred to NASA and Joint Administration, what was known as the Space Nuclear Propulsion Office, and the Atomic Energy Commission. And the testing of the reactor designs that would go into this were done at the Nevada test site. What does that look like in concept? This is what a nuclear reactor using hydrogen as the coolant and propellant might look like, did look like. While I was there then in 64, summer of 64, this is what was happening. Kiwi was the reactor design named after the flightless bird, the kiwi. So you saw that in cutaway, what it might look like. This is what it looked like in actuality. And this was at the test cell. Here is one, that reactor firing up. And of course, hydrogen is very explosive. So, as I said, this is a test, and all tests are not necessarily successful. So I actually saw this blow up from an underground, on closed circuit TV, from an underground location.
So it was unexpected.
This was unexpected. Yeah,
Is that the
right.
kiwi? What's left of it?
But you learn something from all of these tests. So apparently they did reach a point where, after several design iterations, of one that was considered feasible. And this is the test cell location. Actually, this was down at Area 25, much closer to Mercury, the residential location. Then the portion that I was involved in, once you have a reactor that is considered suitable for that design, then you have to incorporate it into an actual rocket engine, and you have to have a facility that can static fire this, as all rocket engines are static fired. They don't go immediately into production. So the company that I was working with had the instrumentation and control wiring design for this experimental test stand 1, ETS-1, and there were actually 2 of them. When I was there in the summer of 1964, obviously nobody consulted me on what needed to be done. I carried lots of stuff and took notes on things that needed notes taken on them. But this was the experimental test stand, and that is the storage facilities there for the hydrogen, which would be used in the static firing. This phase of the Rover program was called NERVA, Nuclear Energy for Rocket Vehicle Application. And that was visited in 1963, the summer of 1963, President Kennedy, who would be assassinated within just a few months following this picture that you see right here. No, he did not come over to my trailer and have chicken dinner with me while he was there.
Did you see him when he was there?
Pardon?
Did you see him when he was there?
I did not. No. Our roles would not have brought us together naturally.
Just walking around, maybe you could.
No, not so much. In the late 1960s, the rising cost of the Vietnam War put budget pressures on Congress, and many marginal or controversial projects, and this was certainly one of them, such as Rover, were defunded. It was rescued in various forms because it had some political allies in Congress. It was hard to cancel it out, but it was formally terminated in 1973. But I have been reading recently, the concept lives on, and there is renewed interest. I don't know any details on that, but I have read about the renewed interest in developing a nuclear rocket engine. So the good ideas interesting ideas will never entirely die. And I think this is one of them. And it was just such a pleasure to be on the ground, both for the tunnels and the nuclear program. I would remain terribly impressed by the people that I worked with. These were not amateurs. This was some of the best minds, I think, I have ever known in science and engineering. And what an interesting time to have been a small part of that. So much for the summers of, my summers of 62, 63.
Speaking about summers, what was it like to work in that environment?
It was hot.
Yeah.
These guys in suits.
But some of the guys that I told you about, the tunnels engineers, if they had days off, their idea of a good time was to put a couple of cans of soda under an old vehicle, four-wheel drive vehicle, and head out into the desert and go explore some of the old mercury mines out there.
Even your offices, with the air conditioning.
Yeah, oh yeah. The underground, of course, was cool, about 50, 55 degrees, way back in those tunnels. They did experiment initially with shafts, but think about the size of a shaft operation that would allow you to get equipment needed for testing down there. And also, whereas you can, by design, you can contain the energy and contamination in the tunnel, you can't do that in the shaft. It blows up and out, period. So that's why tunneling instead of shaft testing. They toyed with it, they tried it, but it ran into its own problems.
Why don't we ask Mary Ellen or
Mary
Sam
Ellen,
if they have a question?
you have any questions?
I had a quick one for Bill, which had to do with maybe the protection outfits that you were provided. You talked about the one incident, I think in the J Tunnel, 1963, and you had to run or get into a vehicle and run away. But I was thinking for hearing or some sort of a suit and so forth. Did they provide that for you?
Did they?
We did provide the suit for the contamination control.
No, we were just washed, scrubbed, chemically treated. No,
Wow.
no.
Dials. It's good enough for the birds.
Surface.
Can you say that crap when I'm?
And then they'd run the counter over you and satisfy themselves eventually that you were going to be okay.
And you said that took 2 weeks?
2 days. 2 days. Yeah, and they were able to get the radiation, measurable radiation,
Right.
down to an acceptable level in that time.
Do you know if anyone practically used nuclear excavation?
No, to my knowledge.
Unless you count the craters.
I think there were talk about building another Panama Canal with that method.
Yeah.
I remember when I was in college, I took an environmental course about 1973, and I remember seeing the map of bringing this water down.
North American Water and Power
Yeah,
Lines.
that was a concept.
Well, it's all downhill, right?
Yeah.
Kind of an oversimplification, but yes. But there were, with a few connections that could have been made between valleys, that had the potential. Think about 75 million acre feet of water a year. I mean, that's a lot of people. Chances of something of that magnitude ever getting all the boxes checked and all of the people satisfied that have to be satisfied are pretty remote.
Okay. Well,
Sit down.
Yeah, good job.
Thank you.
Okay.
thank you, Bill.
Yeah, my pleasure.
All right. Well, that concludes our program for Friday, May 25th? 26th? Okay, 26th. Thank you all for joining. I'll hope to see you again in 2 weeks.
Engineers and architects of Hawaii welcome your comments on this program and any of our recent programs. We encourage your direct participation in this community outreach. So please email us your comments and ideas at eahawaii@gmail.com.